last class we discussed about common emitter amplifier. Now, today we will be discussing other type of amplifier like common base and common collector amplifier. So, common base amplifier has the base common to both the input and output circuits. That is, the input circuit is between the emitter and the base, and the output circuit is between the collector and the base is grounded. So, let us discuss a common base transistor amplifier. So, in this common base transistor amplifier, we are having two DC sources VEE and VCC. Now, these sources are there for biasing the transistor in the forward bias as well as the reverse bias conditions. That is, the emitter base junction will be forward biased by VEE and the collector to base junction will be reverse biased by VCC. Now, there are two different sources here, and the resistances which are connected from emitter are RE and collector has a resistance RC, and the source Vs, which is a weak signal which has to be amplified, is coupled by the coupling capacitor C1, and the source has a resistance Rs in series with it, and the coupling capacitor at the output side is C2, which couples the output voltage. That is, it prevents the DC voltages and only allows the AC voltage. That is the reason for connecting these coupling capacitors. We are taking, for example, a PNP transistor, which is indicated by the arrow mark in the emitter base junction, and that is why the polarities of the DC sources VEE and VCC are like this, and emitter base is forward biased by VEE and collector base is reverse biased by VCC. So, in order to analyze this common base transistor amplifier, as usual we will have to draw the AC equivalent circuit, and we will have to incorporate the transistor model, that is the RE model we are discussing. That model will be replacing the transistor. So, we will be doing that, and we note that there is a load resistance at the output across which the voltage available is V0, and that voltage is the output voltage which we get after amplification. So, in order to draw the AC equivalent circuit for this amplifier, following the usual procedure, that is, of course, we will have to first short circuit the DC voltages, make them 0, and the capacitances are assumed to be quite large, so that under the frequency of operation, that is the frequency of the signal Vs, these capacitors are offering short circuit path. So, following these steps, we will be now drawing the AC equivalent circuit for this amplifier. So, here these two DC sources VEE and VCC will be grounded or made them 0. The capacitors C1 and C2 will be now short circuited, and amplifying circuit after drawing this AC equivalent circuit will be looking like this. So, here this DC sources after removal, we are left with this circuit, and the capacitors are also removed because they are short circuiting, and the source is Vs along with this resistance Rs, and we are having this resistance Re and Rc. So, Re is here in the emitter and Rc is in the collector, load resistance is there RL in the collector side, and the transistor is being replaced by the RE model. So, this part is the transistor model. So, here we have this resistance RE, the emitter base forward bias resistance RE, and the current which is flowing through RE is the emitter current IE, because it is a common base transistor, base is grounded and it is common to both input and output circuit, and input at this point emitter is the input current IE, and the collector current is at the collector or output, which is IC. And remembering the relation between the collector current and the emitter current for a common base transistor, we know that IC by IE equal to alpha. The current amplification factor for the transistor in common base is denoted by alpha. The alpha has maximum value of 1. So, IC is equal to alpha times IE. That is why IC can be assumed to be a current source, a dependent current source whose value is alpha times IE. That is why we are writing alpha times IE in the dependent current source, and the direction of current for this PNP transistor is this, that is, it will be going out of the device and input current IE is coming into the device. So, this is the AC equivalent circuit. Now, here one thing to note is that we are ignoring R naught, that is, the transistor output resistance R naught is here neglected, since we know that for a common base transistor the output resistance is very large, even larger than the common emitter, and we have seen earlier that the current in the output, that is the collector current, is almost horizontal with respect to the collector base voltage, and we were having actually almost horizontal characteristic curves in the output characteristic, that is without any slope. So, even though we change VCB, there is not going to be any change in the collector current. That is why we can very well assume that this resistance, which is actually present in the output of the transistor, that is the characteristics, output characteristics will give us the output resistance, but that is very large, almost equal to infinity we can assume. Because it is very large, practically it is like ignoring it will not be affecting anything, because if this is very large, R naught is very large, even though if there is a resistance R naught whose value is very large, no current can flow through this R naught because of this property that it is very large, almost equal to infinity. That is why we are ignoring it conveniently in this circuit. So, now from this circuit we can proceed to find out all those parameters. So, the parameters of interest here are the input impedance, output impedance, voltage gain, current gain. So, we will be finding out input impedance first. So, the input impedance means the ratio between the input voltage Vi and the output voltage input current II, that is Vi by II will be giving the input impedance and replacing the value of Vi. Now, if we consider this circuit and find out what is this voltage at this point Vi input terminals, it is equal to the current flowing through this Re multiplied by this Re. So, Vi is equal to IE into Re. This is the input voltage, or we can also write it in another way, that Vi is also equal to the current flowing through this resistance Re into Re. But in any way if we write, ultimately we will be getting the same expression, because what is IE? In terms of II, if I write IE is nothing but II into Re by capital Re by capital Re plus small re. So, this is the I current multiplied by small Re. So, even if you take this other resistance and find out the current, it will be II into Re by Re plus small re into capital Re. So, that will be giving you the same expression. So, after writing down V I equal to II into Re by Re plus Re into small re divided by input current II, we can now cancel out these two, the II cancel out. So, what will be left with is the input impedance Re by Re plus small re into small re, and that is nothing but the parallel equivalent resistance between Re and small re. So, we have now the input impedance is the equivalent impedance between the two parallel impedances, capital R capital E and small r small e. That is very evident if we look from this input terminal into the transistor input circuit. We are having two resistances parallel, one point it is connected to emitter, other point is ground. So, these two are parallel resistances. So, we have this parallel combination as the input impedance, and mind it here actually, although I am using the term impedance, but basically all are resistances. So, Zi is nothing but actually resistance input, because there are no other components like capacitance, inductances, etc. Here only pure resistances are there. So, input impedance is nothing but input resistance, which is R capital E parallel small re. Now, one thing to note is here is that out of these two resistances, Re is very small, it is in the order of ohms, whereas typically the value of Re generally is in the order of kilo ohms. So, as we know, whenever we have two parallel two resistances in parallel, one is having a large value and the other is having a small value, the equivalent resistance approaches towards the smaller value. So, this parallel combination will be giving almost equal to Re value. Even numerically also we can do and see it, but this is just to bring out the fact that input impedance of the common base transistor or input resistance of the common base transistor is very small. It is because it is almost equal to Re, and Re we know the emitter resistance in the transistor model, that is having a value of around some ohms. So, input impedance is or input resistance is small in a common base transistor. Now, the output resistance or output impedance, if we find out, look into the amplifier from the output terminals. So, we have to look from this point to find out Z0. From the load we will have to look, excluding the load. So, if we want to find out what is the output resistance or output impedance, we will look from the load into the output circuit, making the input source 0. So, Vs is made 0, whenever Vs is made 0, IE will be 0, so IC will be 0. We are left with this circuit having only RC resistance. So, the output resistance is RC, output resistance or output impedance of this common base transistor is RC. So, we have found out input impedance or input resistance and output impedance or output resistance for this common base transistor. Next, let us find out what is the voltage gain for this common base transistor. Now, voltage gain we know it is a ratio between output voltage and input voltage. That means, we have to find out what is V naught by Vi. So, again looking into the circuit, find out V naught by Vi. Now, V naught is what? V naught is equal to minus I naught into RL. V naught is equal to, because this point is positive, this point is negative as far as V naught is concerned, but we are finding out I naught into RL. I naught is basically flowing this way, this is I naught is this one. So, from bottom to top. So, its direction is reversed than what we are assuming for V naught. So, it will be minus I naught into R L. Now, again what is I naught? I naught is nothing but that part of the current which flows through this resistance R L coming from this source or independent source alpha I e, because we see here alpha I e is divided into two parts, one is going through R C, one is going through R L. So, the part of the current which goes through R L is basically alpha I e into R C by R C plus R L, but the direction is opposite to I naught. So, if I find out that part of the current, it is I C is basically one part is flowing through this and one part is flowing through this, but we have assumed I naught to be in this direction, conventionally that is done like that. So, again I have to have a minus sign. So, this I naught is basically minus I C into R C by R C plus R L and multiplied by R L. So, ultimately it will be positive. So, it is I C into R C parallel R L is the V naught. Again what is I C? I C is equal to alpha times I e. So, replacing again I get alpha times I e R C parallel R L, this is the output voltage. And input voltage is again using the earlier expression that we have already found out what is input voltage, that is I e into R e. So, input voltage is small I e into R e. Again I e is nothing but we can replace by I into R e by R e plus small r e. So, the whole thing multiplied by R e. So, what we get is I e I into this is I into R e parallel R e. So, these two are the expressions what I get from V naught and V I, and so replacing the thing here, that is we are getting it alpha times R C parallel R L, this is this output voltage, and it is R e parallel R e, this input is I e parallel R e. So, I e can be cancelled out. So, instead of putting it into or expressing it into again I with respect to I, let us keep it here. So, the upper portion or the numerator for this voltage gain, output voltage V naught, that is equal to alpha times minus minus becomes plus. So, alpha times I e into R C parallel R L, and the denominator becomes I e R e. So, I e cancel, what we get is a alpha into I C parallel R L by R e. And one thing to be noted here is that in the voltage gain of common base transistor amplifier, there is no negative sign in the expression, meaning that there is no phase reversal or phase shift occurring in the output voltage with respect to the input voltage. That is different from a common emitter amplifier, because in common emitter amplifier we have seen that the phase reversal of 180 degree takes place between input and output voltage, but then here there is no phase shift as far as the voltage is concerned. Now, if we want to find out what is the overall voltage gain, similarly as we have done earlier, it is equal to the voltage gain A V multiplied by Z I plus R S. Now, current gain, in order to find out, we will be using this expression for current gain is I naught by I, output current by input current. Now, output current I naught is what? Output current is again the part of the current which flows through R L, and this part of the current which is coming from I C, but it is in the negative direction, because I C is having one part here and the other part here. So, So, this part is just opposite to the conventional direction of I naught. So, we can write it as minus I c into R c by R c parallel R L, and I, let us keep it as I. Now, again we can write as I c as alpha times I e, R c by R c parallel R L, and I. So, proceeding in this manner, we have a minus sign here, that has to be noted. So, it is minus alpha I e into R c by R c plus R L. Again I can write down this I e as that part of the current, input current, which flows through R e, and that is equal to I I into R e by R e plus R e. So, I I into R e by R e plus small r e. So, replacing this I e in the numerator by this expression, we get minus alpha into I into this whole term and this term, and the denominator is having I. So, now I can cancel out I and I. So, here the final expression for this current gain is obtained, and here we have to note that the current gain is having a negative sign. That means, the current at the output and the current at the input, they have a phase reversal of 180 degree. The voltage does not have a phase reversal. Output voltage and input voltage are in same phase, but the current at the output and the current at the input I naught and I that have a phase reversal of 180 degree, that is denoted by this minus sign. So, here this current I in this direction, the current I in this direction. So, if we compare them, I naught by I, that has a negative sign, because of this fact that they have a phase reversal. Now, where this common base amplifier is mostly used, actually the common base amplifier is very frequently used as a current buffer. So, the current buffer means, suppose we want to use the common base amplifier as a buffer stage between a source and a load. Now, when we will be wanting to use it as a buffer transistor, because when we have a load very small as compared to the resistance which is in parallel with a current source. Suppose for example, in this circuit we are having a current source having a current I, and we know that all current sources are having a resistance parallel to it. Ideally that should be infinity, because then no current will flow through the RS, all the current will flow through the load, but practically that does not happen, because the resistance which is in parallel with the current source is generally having a value less than infinity. So, what is happening here is that this load RL is getting a current I minus IRS. IRS is the current which flows to this source resistance which is in parallel with this current source, and a part of it is only going through RL. Now, if the load resistance is very small, but the source resistance RS is very high. For example, a typical case can be thought of where we are applying the output voltage to a loudspeaker. For example, loudspeaker has very small resistance, it is maybe 2 ohm, 4 ohm like that, and if this source resistance is not infinity, then what will happen is that the current which will be flowing I minus IRS, as this is not equal to I, then we have to basically think about something where we will be getting the whole amount of the current I, and for that what is done is that there is a buffer stage common base amplifier, and that buffer stage is included between the source and the load. Now, what will happen if we use a common base amplifier? Because common base amplifier has a input resistance which is very small, because it is equal to almost equal to Re. So, now this current source has a small resistance at the input of this transistor. There are two parts, but this has a very small value as compared to Rs. So, mostly all the current will flow through this small Re, and this Re being very small as compared to the source resistance of the current source, almost all the current will flow through Re. Now, the common base amplifier has a current gain of maximum value 1, that is alpha can be this gain of this common base amplifier current gain, if we consider its value can be maximum will be 1. So, if we consider this output current alpha times of IE is this current, IE means this current, and that current is equal to the input current now. So, alpha times of IN is the current here at this current source, and almost this is equal to IN, because alpha is almost equal to 1. So, what we get is here this current IN is same as current I, because of this fact that all the current is passing through this Re. So, I in equal to I. That means this load is getting the current I, practically it is getting the whole of the current from the source. So, that is why common base amplifier is effectively used as a buffer stage in this type of examples. That is when we want to get all the currents from a current source in a load, then we can use it as a buffer. Now, another amplifier which is used is common collector amplifier. Now, common collector amplifier has the collector as common to both input and output circuits. Now, how this collector is common and grounded, that we will have to look for. First of all, let us discuss the circuit of a common collector amplifier having a resistance Rb, biasing resistance, and this circuit looks familiar with the common emitter amplifier, but only thing is here that the collector is not having any resistance Rc, is directly connected to the source Vcc, that is the biasing source, and the voltage is obtained across the resistance Re which is connected to the emitter. We are not getting the voltage across earlier, as in earlier cases. We were getting the voltage between collector and ground, but here between emitter and ground we will be getting the output voltage, and this load resistance is also between emitter and ground. But other, as far as the biasing is concerned, it is similar to that fixed biasing circuit of the common emitter amplifier. Now, how it is common collector amplifier, that means how this collector is common. In order to understand that, let us first draw the AC equivalent circuit for this amplifier. If we draw the AC equivalent circuit following the usual procedures, we will be making the Vcc source 0 or grounded. So, collector is directly grounded and the circuit will be looking like this. Here we are considering a NPN transistor. So, the emitter side, if we start from base, this is the base point, this is the emitter, this is the collector. Base is having this resistance Rb, here base is having this resistance Rb to ground, because Vcc is grounded, and B is also through this short circuited part. After eliminating this capacitance C1, it will be having the source resistance and the source. So, this is the source resistance and the source Vs. Now, the collector is directly grounded and Rc is also not there, so it is grounded, C point is grounded, and emitter is having the resistance Re, because in this circuit if we look, emitter is having this resistance Re, this capacitance C2 is shorted. So, it is having this resistance RL also, which will be now parallel with Re and connected to ground. So, this is happening here, RL and Re are parallel and connected to ground, Now we understand how this is called, why this is called common collector, because if we look into the input and output circuits, input base and this point is having the input circuit. This point is what? This point is nothing but this collector point. Collector point is directly grounded. So, as if collector is grounded. So, we are having the input circuit between base and ground where collector is grounded, and the output circuit is between, output circuit means we are getting the voltage across this resistance Re which is connected to the emitter. So, the output is between emitter and collector, collector is grounded. So, this is one part of the circuit, output circuit, this is input circuit, this is input circuit, this is output circuit. So, input circuit is true, this is the whole loop, and output is, whole loop is this one. So, here it is clear that the collector is common, this point is a common point which is grounded, and that is nothing but this collector, this point is collector and this point is same. Now, a circuit, this circuit is a bit different. In order to analyze it, we must be careful, because the current which is flowing, you see this current which is flowing through this base emitter circuit, that is the transistor is being replaced by its model. So, the emitter base junction as usual is having that resistance beta plus 1 Re. So, the current which is flowing through this beta plus 1 Re is Ib, and the point emitter, from this point the current which is flowing is emitter current is beta plus 1 Ib, and this is the collector current which is beta times Ib. Beta times Ib and Ib are joining here to give rise to the total current which is the emitter current. Now, the analysis of this circuit can be easily done to find out all those parameters like input impedance, etc. Input impedance can be found out by looking into the input circuit from the input terminals or from the source rather. So, if we look from this side Zi, then we will have to get the input impedance considering this circuit, but you have to be careful, because here the input circuit is having Rb as well as this resistance beta plus 1 Re, and there are two resistances in parallel, not only single Re. That point has to be carefully noted, that at this point we have the two resistances Re and Rl in parallel. So, in order to find out the input impedance, if we want to find out input impedance by taking the ratio between Vi and Ii, what is Vi? This voltage from base to ground or collector, that is grounded. So, the voltage from this point to this point is Ib into this resistance, that is Ib into beta plus 1 into Re, plus voltage drop from emitter to ground, and the voltage drop from emitter to ground is beta plus 1 Ib into the parallel impedance or parallel resistance between this Re and Rl. So, doing that we find what is Vi. Vi is equal to Ib into beta plus 1 Re plus beta plus 1 Ib into Re parallel Rl, and that can be combined, of course, that taking common Ib and beta plus 1 we can get Ib into beta plus 1 into small Re plus Re parallel Rl. So, this is the expression for Vi. Now, we can find out the value of resistance at the base to ground, that is denoted by Zb. Just to simplify the matter a bit, let us find out what is Zb. Zb, if I look from this point, that is the resistance between input impedance or input resistance between this and this point. That means, it is the ratio between the voltage Vi and current Ib. So, Zb is Vi by Ib. Again, Vi is beta plus 1 into Re plus capital Re parallel capital Rl, because Vi is this whole thing divided by Ib, Ib cancel. So, this will be remaining. Now, if I want to find out Z I by V I by I can very simply write down what is V I. V I from this expression I can put down. So, that is equal to I B into Z B. I B into Z B is V I divided by I and that is equal to I B again can be written as I into, this is I into R B divided by R B plus Z B. So, this is what we are doing, I into R B by R B plus Z B into Z B divided by I. Then these two cancel. What we are left with is this expression is nothing but R B parallel Z B. If we replace Z B by this value, then we get the final expression. Now, one thing to be noted is here is that the Z I or the input impedance or rather input resistance is high in this common collector amplifier, because both the values R B and Z B will be high. Since Z B is what? Z B is equal to this beta plus 1 into this thing and R E plus this parallel impedances. Parallel impedance will be having an order higher order. So, the whole thing will be high. That means, even though it is parallel with R B is again having a high value in the order of kilo ohm generally. So, the value of this Z I in a common collector amplifier is high. And next we go to find out what is the output impedance and all that. So, after input impedance we will be finding out again say the voltage gain. Voltage gain is V naught by V I. V I we have just now calculated, that is I B into beta plus 1 into R E plus R E parallel R L, and V naught, if we look into the circuit, find out what is this voltage. The voltage between this point and this point, or emitter and ground, that is equal to the current flowing multiplied by the parallel impedance between these two. In that way, if we look, it is very easy to understand. So, what will be this V naught? V naught equal to the current I E into the parallel impedance R E parallel R L. That is what is done here, and what is again I E, that can be written as beta plus 1 into I B, beta plus 1 into I B R E parallel R L. This is the expression for V naught. So, V naught is equal to beta plus 1 I B into R E parallel R L. So, now dividing V naught by V I, the whole expression by this expression, we will be getting what is A V. So, replacing this, we get A V equal to this divided by this. Now, we can cancel out I B, and finally, we are left, also we can cancel beta plus 1 into beta plus 1. So, we are left with the expression R E parallel R L divided by small r e plus R E parallel R L. Now, if we notice carefully this expression, then we see that the denominator is higher than the numerator, because in the denominator we have another extra term R E. So, small r e plus R E parallel R L, but in the numerator it is R E parallel R L. So, that means we get a fractional value. So, maximum can happen only if R E is very, very small, so that we can ignore, then this will be cancelling out, numerator and denominator will be cancelling out, and then it will be equal to 1. So, what is the inference from this is that the voltage gain maximum value can be 1. So, we generally do not achieve a voltage gain in this type of common collector amplifier, and the overall voltage gain can be found out, multiply A B by Z I by Z I plus R S, that will be giving you the overall voltage gain, means with respect to the source. So, here this point is important, that the voltage gain in a common collector amplifier is less than 1, and maximum it can be only 1 if we ignore this R E totally. Now, output impedance, in order to find out output impedance, we have to first of all look from the output side terminals, make the source 0. So, the same circuit let us consider again, and you make the Vs 0. So, having only the Rs in this input circuit, which is parallel to Rb of course, and this is the transistor. Now, at the output between say AB terminals, let us assume that these are the points at the output we will be considering from AB terminal, output terminals. Find out the output impedance for this transistor amplifier circuit. So, we are having at the emitter this point, if we consider focus on emitter, and between emitter and ground, what do we have? We have a resistance Re, we have a load resistance RL. So, now in order to find out the output impedance, looking from this AB terminal into the circuit, we will be having an output impedance Z naught dash. That Z naught dash will be coming in parallel with Re, and that will be giving the exact or the final output impedance. So, overall output impedance for this amplifier is Z naught dash parallel Re. So, Z naught equal to Z naught dash parallel Re. Now, what is Z naught dash? We have to find that out. Now, in order to find out what is this output impedance Z naught dash, we have to apply a source, because we see that we have made the source Vs 0. So, if we apply an external source, that is the procedure to be followed. Apply an external source at the output, which is Vx, and due to this Vx the current flowing say is Ix, then we have to find out Vx by Ix to know what is Z naught dash. That is, we have to find out the expression between Vx and Ix, that will be giving you Z naught dash. That Z naught dash will be in parallel with Re, that will give the actual output impedance of this whole transistor amplifier. So, let us do that. If we apply an external source from outside, we are applying Vx. I am not bothered about what exactly the magnitude of voltage, because that is not necessary, because we want only the ratio between Vx and Ix. So, Vx when we apply, the current flowing is say Ix. At this point the current is divided into two parts. One is this base current, the other is this collector current. So, we can write down that Ix equal to Ib plus Ic, and again Ic is equal to beta times of Ib. So, the whole expression becomes Ix equal to beta plus 1 Ib. Now, what is Vx? This voltage equal to the voltage between these 2 points is equal to the voltage between these 2 points, that is this drop plus this drop. So, this voltage drop is what? Ib into beta plus 1 Re plus Ib into the equivalent resistance between Rs and Rb. So, that is what is Vx. So, Vx equal to Ib into beta plus 1 Re plus Ib into Rb parallel Rs. So, we can now write down what is Ib. Ib is equal to Ix by beta plus 1. Replacing this Ib by Ix by beta plus 1, then writing down the other terms, the common terms is Ix by beta plus 1. So, what will be left? Left out terms in the bracket will be beta plus 1 into Re, because we are taking Ib common and replacing that Ib by Ix by beta plus 1. So, it will be beta plus 1 into Re plus Rb parallel Rs. So, Z naught dash is equal to Vx by Ix. Taking this ratio between Vx and Ix, what we get is equal to Re, beta plus 1 cancel for this term. So, Re plus Rb parallel Rs by beta plus 1. That is Z naught dash. So, in order to find out Z naught, it is parallel with Re. So, that is the output impedance or output resistance for this common collector transistor amplifier. And here one thing we can note is that the value of Z naught will be low, since this Z naught is Z naught dash parallel Re, Re is a high resistance, no doubt, but then what is Z naught dash? Z naught dash is equal to Re, small re plus this term. Now look into this term, it is a term which will be having its parallel resistance Rb and Rs divided by beta plus 1. Beta plus 1 is generally a high value. I mean it will be, the denominator will be having a high value, and the numerator is of course it is in the kilo order, but then overall term will be not very high, and it is plus small re. So this term Z naught dash is smaller in comparison to Re. So it will be approaching the smaller term, means Z naught will be a small value. So Z naught is low for common collector amplifier. So for common collector amplifier, what we have noted is that the voltage gain is almost equal to 1, the input impedance is high and output impedance is low. Now these facts can be used effectively when we want to use the common collector amplifier as a voltage buffer. That is, common collector amplifier is used as a voltage buffer because whenever we want to apply a voltage source to a load where the source resistance of the voltage source and the load resistance have a mismatch. That is, suppose we are trying to apply a voltage given from a voltage source, a common emitter amplifier. We are using a common emitter amplifier as a voltage source, and we know that common emitter amplifier has a output impedance high. So the resistance or impedance which will be in series with that voltage source will be having a high value. But suppose we want to apply this to a low load like a loudspeaker, it is having a 2 ohm or 4 ohm etc., the small value of resistance in the loudspeaker. Then what will happen is that how much voltage it is getting? It is getting only Vs into RL by Rs plus RL. If we look into this term, RL is small, this is big because it is plus Rs. Rs is having a high value, source resistance. Of course, ideally it should be small, but it is not, practically we do not get a zero source resistance. What we have, depending upon the source used, suppose we are using a common emitter amplifier, the source resistance will be the output impedance of the common emitter amplifier. Then this whole term will be having a small value because the denominator is higher than numerator. So this will be a portion of Vs what we will be getting at the output. That means V naught will be having a small portion of Vs. We are not getting exactly Vs, but our intention is that we must get the source voltage wholly at the load. In order to transfer the whole source voltage to the such type of low loads, we generally incorporate a buffer stage between the source and the load, and that buffer stage is common collector amplifier. Now why this common collector amplifier is being used? There has also particular reasons. So look at this circuit. Here this common collector amplifier is inserted as a buffer stage between the source and the load. Now we are applying a source Vs having a source resistance Rs. Rs is high compared to the load resistance RL, where we want to get the source voltage totally equal to Vs. So now the common collector amplifier, just now we have studied, it has certain specific parameter values because we have seen that the common collector amplifier has a high input resistance, Ri is high, but it has a low output resistance, R naught is low, and the voltage gain is almost equal to 1. So if I replace this common collector amplifier by its equivalent circuit having the input resistance, output resistance and voltage gain, it can be drawn like a circuit given under this dashed box. Here is having Ri, this is the output voltage V naught, or say V naught dash, rather we are using V naught here. So let it be V naught dash is the output voltage from the common collector amplifier, and this is equal to nothing but AV into Vi. Now that is almost equal to Vi because AV is equal to 1. Now what is Vi? Vi is the voltage available across Ri. Now since Ri is a high value, so whatever voltage we will be getting here, it is almost equal to Vs. since we have seen that Vs into R, here if we again write Vs into Ri by Ri plus Rs, this will be your Vi. Now, if this is high value, then we can, this is higher in comparison to Rs, we can now equivalently write that it is Ri by Ri, that means this can be cancelled out if Rs is small in comparison to Ri, that has to be maintained. And as Ri is having a high value because it is a common emitter common collector amplifier, so that can be actually managed to have a value higher than this source resistance, and then this whole overall term will be almost equal to 1. So, what we will be getting here at Vi is equal to Vs. So, that means this Vi is equal to Vs, again there is a very small resistance at the output which is R naught. So, there will be practically very less drop, almost 0 drops say. So, whatever voltage available here, that will be wholly available at the output. That means the load resistance RL will be getting the voltage which is equal to Vs, because this is Vi, Vi is again almost equal to Vs. Out of Vi only a very small portion is lost here. So, the whole voltage we can get at RL. That means we are incorporating a buffer stage which is common collector amplifier, which is known as voltage buffer, just to get this source voltage totally equally at the output. So, now we have seen this application. Now, in order to know about how the solution of a particular amplifier circuit, means what you want to find out different parameters, suppose let us try one example here, and this example is common emitter amplifier example, and we are having all these values like shown here. But one thing to be noted is here that we are not having a source resistance, and we are, that means Rs is equal to 0, source is having 0 resistance, and we are having a load resistance also. So, now in order to know the no load voltage gain and the loaded voltage gain, that means for this amplifier circuit you have to determine AV no load, AV load, Zi, Z0 and Ai. So, in order to solve this circuit, no load means whenever you have 0 load here, the load RL is not here, that means we will be having no load voltage. Whenever you will be applying the load RL, then whatever voltage available will be load voltage, and there is a difference. When RL is coming into the picture, the RL will also have to be included, and that changes the voltage gain, and loaded voltage gain will be less than no load voltage gain. That can be verified for this circuit actually. So, in this circuit, in order to know all these parameters, because we have already discussed about these circuits and we know what is Zi expression, but then everywhere you will have to use this Re value. So, Re is 26 millivolt by capital I capital E. So, that has to be found out, and in order to find out this, we have to consider the DC equivalent circuit. So, DC equivalent circuit has to be drawn first. So, DC equivalent circuit means you ignore this AC sources and you ignore these capacitors also, because capacitors offer open circuit for DC. What will be left with? We will be left with these resistances. These are the potential divider biasing scheme, RC and RE will be there. This will be just open circuit, this will be also open circuit. So, we are left with the circuit which is like this. This is VCC, R1, R2, RC, RE, and this is a common, this is a NPN transistor, common emitter NPN transistor, and beta value is given as, beta value is to be given which is equal to say 100. So, now this beta is 100. So, now the currents are IC, this is IE, and using the Thevenin's equivalent circuit we can draw this Thevenin's equivalent circuit. This Thevenin's equivalent circuit will be having this resistance R Thevenin and voltage V Thevenin, VCC, RC, RE. Now we know what is V Thevenin and R Thevenin. R Thevenin is the parallel impedance between R1 and R2, and V Thevenin is VCC into R2 by R1 plus R2. So putting these values here, because VCC is equal to 16 volt, it is given as 16 volt. So V Thevenin is 16 into all these values you just replace. R2 is equal to 16 kilo ohm, R1 is 68. So we will be getting 16 into 16 plus 16 plus 68, and that gives, just check these values, 3.05 volt. We will be getting the V Thevenin, and R Thevenin is this 16 into 68 kilo ohm, and that will be giving, the value will be 12.95 kilo ohm. So we can now find out in this circuit, if we look into, I can find out base current, I can find out the collector current and emitter current, because Thevenin's voltage, Kirchhoff's voltage law, if we apply to this circuit, then V Thevenin minus IB into R Thevenin minus VBE minus IER is equal to 0. So if we do that, V Thevenin minus Kirchhoff's voltage law we have to apply, minus I Thevenin into IB, not I Thevenin, this is base current, into R Thevenin minus this voltage drop VBE. If we look into the circuit, you cannot ignore this voltage drop between base and emitter, minus IE into RE, that equal to 0. So putting all these values, we get IB equal to 0.0265 milliampere, and what will be the collector current from this we can find out, and base current also we can find out. Base current is equal to beta plus 1 into 0.0265 milliampere, and beta value is 100. So we get, the value will be 2.677 milliampere, and so we can find out what is the RE value, that is 26 millivolt by I is 2.677 milliampere, and that gives us 9.71 ohm. Once we know RE, we can plug in this RE wherever required in our analysis of finding out these parameters. Of course, here if we consider the no load voltage, AV no load, we will have to look into the circuit to find out the no load voltage, and no load voltage and loaded voltage will be different, because no load voltage will be having no load here. So the circuit will be having only RC, and R naught is not mentioned. So we will be finding out that no load voltage as V naught by Vi will be equal to minus I naught into RC by Vi. Vi is IB into beta plus 1 RE. So here this I naught can be written as beta IB into RC by IB beta plus 1 RE. So then IB cancel. So this is the value of the no load voltage gain, whereas the loaded voltage gain is with respect to, with taking into consideration load resistance, that we have already done. So we can find out the difference. So now in this lecture we have today learnt about the common base and common collector amplifiers, and the common base and common collector amplifiers have application as current and voltage buffers. But for amplification, we have earlier discussed about the common emitter amplifier, which is mostly used as an amplifier. So, we have totally seen all the different examples of amplifiers using BJT.